So let's continue on this hierarchical design methodologies. So the technique that is used to create a complex and larger design, right, was introduced to you in chapter 1, in the first chapter, in the design philosophy, right? So in hierarchical design methodology, what we will do is that we will use our previous design to create another design, and especially a larger design, right? So this is a very good example to demonstrate the hierarchical design methodology. So for example, when we want to design a very important circuit in data circuit, which is an adder, okay. So this is the circuit of half adder, right? So an adder is a circuit that can add numbers, right? For example, if we have two numbers we want to add and get the result, so we will use the adder, right? So this is a half adder, a circuit of half adder, and we can create a block like this. Yeah, this is the gate level schematic. So we have A, B, and we have the output S and C, sum and carry. And we can use this half adder, right? We connect with another half adder, and we have another input called C in, like this. Yeah, because full adder, in full adder, yeah, half adder is not very useful because it cannot be used to create a bigger adder, right? Because normally we add not one bit number, not only one bit number, but we have many bits number, yeah, 2 bit, 3 bit, 4 bit, 8 bit, and so on. So for that we will use the full adder. So full adder, you need another input called C in, okay, and we can create a full adder using the half adder, and the connection is like this, right? We have two half adder, and this is the same half adder like this. Yeah, means that we use the same design and we connect like this, and the output here is connect to the product or S sum, and we have this output from this C, and C we OR, use the OR gate, and we get the C out, right, for the full adder. So here you can see that we reuse the design, right? So this is a kind of hierarchical design methodology, where we can see that in this big design we have a smaller design. This is this one and this one. This is like a hierarchy, right? The big one, and when you uh, break into a smaller design, you can see that there are many other design inside, smaller design inside, right? So here you can create the half adder first, and then do the connection to create like this, to create the full adder. So this is the code to describe the half adder. Okay, so you can describe using the structural modeling, because we have the schematic, right? So we can use the structural modeling as O, as AB, as AB, and we have N, C, AB, and C, AB. So we have this half adder, and to create the big circuit like this, we can use the module instantiation. So if you look at the first, where is our first? Yeah, the first lecture here. Oh, not the first, the second one. Sorry, this one. when in the first part of this, you have this module instantiation, right? This one. So what we do here is that we instantiate this half adder into a new design here. All right. So we have a smaller design sub module here, and this new module, new circuit is called FA, and we have A. This is A. We have B. This is B. We have CI. This is CI, and we have CO. This is CO, and we have S. This is S. And we need to describe all the input and output, and all, of course, the wire. So we have output as CO, input ABCI, and we have internal wires. So this is internal wire W1, W2, W3, right? And all are 1 bit in size. Now, how to have this? To have this, we can call, this is how we call our previous design, right? Call the name of our previous design, HA. HA is this one, right? Because our previous design, our name, the name is HA. So this is HA, right? And we need to have a name for this module. We name it M1, all right? Or you can name it using other name, up to you. In this example, we use M1. So this is M1. And we do the connection. So how to do the connection? There are two type of connection, yeah, that we can use. The first one is, we call it name port connection syntax, and the second one is called positional port connection syntax. Look at the first one first. So to connect, for example, we want to connect this A to this A, all right? And of course, this A is from our previous module. So the way is to use dot, yeah, A, and we connect to A. This is how connect to A. And for this dot B, connect to this B. This is how. And for this S, dot S, connect to W, W1. So we have this, and this is C, connect to W3. Done. So we have this one. And we want to create this one now. Right? So to create this one, we can call the same module, which is HA, right? HA. So same module here, HA, but the name for this one should be different from this one. You cannot use M1 anymore, because M1 is referred to this. Now we refer this as M1. This one, we call it M2. So this is M2. And do the connection again. So this A is connected to CI. A connected to CI. B connected to W1. S connected to this S. A small s connect to the capital S. And C connected to W2. Right? Done. This one. And we need to create this. So here you can create using structural modeling, or you can create using data flow modeling, right? So in this case, we use data flow modeling. We use assign CO equal to W2 or W3, all right? Or you can use structural modeling. This is or CO W2 W3, also the same, right? So this is a port connection syntax, where if you use this, the order for this one doesn't matter. You can have C first here and A at the back, doesn't matter. There is another method, right? We call it positional port connection syntax. And I like you to use this one because no need to have something like this. This one, yeah, this is good, but it looks longer Yeah, you need to type many symbol here, right? Instead, this one looks shorter, but this is you need to aware of the position, because the name is position, means that the position of the port, yeah, must be the same as this one, right? So for example, when we want to instantiate this one, M1, so the connection, because we want to connect this A to the small a, means that the position must be the same as this one. So this is A, right? A connect to A. This B must be connect to this B. B. And this S is connect to W1. So this is W1. And this C is connected to W3. So we have that. And look at the second one, M2. M2, this A connect to CI. So we have CI first. You cannot put W1 first, cannot. Position must be correct as the same as this one. Next, B connect to W1, that we have W1 here. S connect to the big S, capital S here. And the last one is C connect to W2, so we have W2. And here we use data flow modeling, just same as this one. And we have the same circuit, positional, but the name is now positional port connection syntax. And yes, it will create the same circuit for you. So up to you whether you want to use this style of modeling code or this style of code. Yeah, doesn't matter. All right, so that is how we use the hierarchical design methodology. And now we want to write the test bench for our design. So let's, for example, this is our design. Now, how we simulate? Yeah. So the example is was given to you last week and today also. Yeah, in the previous example, the multiplexer, right? Same thing. So if we want to simulate our design, we will we will need the test bench. Okay. So what is test bench? Test bench is this another module that you need to instantiate your module inside here. So your module now, the design that you want to test is called the DUT, design and test. All right, or you can have CUT, circuit under test, whatever. Right, in this case, we call it DUT, design and test. So you have a test bench, and of course, the test bench is written in Verilog code as well. All right, and it is not meant to be synthesized into circuit. The test bench, yeah, the test bench is used to simulate this circuit. And of course, you need to instantiate this circuit in the test bench module, and you do the connection just like this. Yeah, the connection is just like this, where this one must now declared as rack, and this one must be declared as wire. So in our case, the full adder here, this one, this is our full adder, right? So we redraw such that we have a full adder module like this: CI, A, B input, and we have S output, CO output, right? This one, CI, A, B, S, and C out. So this will be in the box, in this box. Now, when we write the test band, so we have the test band. The name of our test band is FATB, and we have this. So we name this these three, or declare these three as a rack and these two as a wire. So the code will be like this. And again, you need to have the time unit, yeah, the time unit of your dashband. So this time unit is used here when you write a time here. So this means this one is 20 nanosecond. So if your time unit is 10 nanosecond here, means that time here will be 20 multiplied by 10 nanosecond, which is 200 nanosecond. If you write 100 nanosecond here, the time here will be 20 multiplied by 100, which is 2000 nanosecond, and so on. Right? This is time precision. So again, this time precision means that your simulator will evaluate the output every 1 nanosecond. Right? If you write 1 picosecond, means that it will evaluate a lot smaller time, yeah, 1000 times smaller than this. So of course the simulation will be a lot slower as compared to this, but it is more accurate in terms of timing. This is the module name, this one, FATB. Yeah, the input CIAB is declared as a rack wire SCO, and this is how we instantiate this design, FA, our DUT. So we call FA, yeah, because we name our module full adder as FA. So we call FA, and the name is DUT or any other name that you want to use. And you need to list all the port here. And of course, this position is very important. You need to look at this. You start with A, B, C, I. So this should be A, B, C, I, and COS, just like this, COS. Yeah, don't change the position because you use the positional port. Yeah, but if you use this doesn't matter, right? Because it's clearly stated that here, for example, this A is connected to A. So it doesn't matter if this one is written here. Yeah, if you change the position, so it doesn't matter because the connection is described here. But this one, the connection is based on the position. So that's why you need to have the position correct. And this here, you instantiate the module. And here you want to monitor, you want to see, yeah, just like what we did before. So we want to look at A, and we want to look in binary. We want to look at B, look in binary, CI, binary also, C out, and S. And we map this A to A, the actual A, B, CI, COS. And these are the input stimulus. Yeah. So starting from time 0, A should be equal to 0, C equal to 0, CI equal to 0. 20 nanosecond, we change from 000 to 001. Another 20 nanosecond means that at 40 nanosecond, we change again until we have this on the combination, and we can see the output. So let's do this together so that you understand better, right? So let's have our design. So we close this design, close project, we create a new one. We use the project wizard. Next here, here we create a new folder. We call it full adder. Oh no, we want to design a half adder first, right? So we have half adder HA. Select. Our module name is HA, half adder. Next, empty project, yes. Add file, not yet. Click next. This one also click next, and just finish. And we have the full header. So we create a Verilog file, Verilog. Okay, and we can write the code. So the code is here. Just copy and paste from this. Where's our full half header? Yeah, we can use this one. Just copy this and have this, and I save. So this is our half header. I save my half header. Yeah, this is half header. Click save. And I want to synthesize, analysis and synthesis. And let's see if we have any problem or not. Okay, looks like the program is okay. So no error. Good. And I think no need to do simulation for the half adder. We can proceed to the full adder and look at that, because the design is quite easy, quite simple, right? Should be no problem. So to save time, so let's close this, and we have a new one. The full adder. So we create a new one, and again here should be in different folder. So let's have FA, and the name is FA. Next, empty project, yes. But now we want to add file here, because we want to use our previous design. So in this case, you need to add, yeah, this is HA. So if you are in the other folder, so you need to go to the one that you want to attach. So this one is HA. So double click that. So make sure that it is listed here. Yeah, HA.v. .v is the Verilog code. Click next. Here should be finished. Done. All right. So wait for a while. Okay, done. Then we create a new Verilog file. Click OK. And again, we can just get the program from here. So which one you want to use? Let's say this one. P. And yeah, let's rearrange a little bit. Okay, so we have this HA and M1, M2. Yeah, based on this, we save, and the name should be FA, and should be in the directory or folder that we for this project, which is FA. Make sure that. Click OK, and we try to synthesize this. Okay, let's see. Okay, so far so good. We have no error and one warning, and of course the warning is okay. So when you look at this, when you have FA, when you go to the project navigator and expand this, you can see that you have two sub module in the main module here. FA, you have two HA. The first one is M1, the second one is M2. You can double click, it will bring you to this, yeah, the previous design. Yes, this is same design. And also you can actually look at the netlist viewer to see the connection. You go to netlist viewer, RTL viewer, you can have this. Yeah, it will show you the connection after that. All right, so this is A, B, C. See, this is A, B, the HA, the our previous module, right? M1. This is M1 and this is M2, and we have, yeah, this one, the OR gate that produced by this this yeah, CO. That is CO. Yep. And we can see that what is inside. This is a half adder that we create before this. Yeah. So that is how to look at this connection. All right. So looks like it's okay now. So we can have our attachment. So to have our attachment, go to new, Verilog, click OK. And of course, we have our attachment already. So just copy our attachment here. This, copy, and I have my attachment. Yeah, arrange a little bit. Have this. Okay, so the name is this. So I just want to save this attachment. Save. This is the name, FATB. Save. Right. And now I want to simulate. So to simulate, you need to do a little bit some setting here. Go to assignment, setting, tools. You need to go to EDA, simulation. But before that, you have to do this. Make sure that some of you may face this issue where you need to do when you first time run the quarters and want to do simulation. You need to have set the path for to the model sim in your quarters. So you need to go to tools, go to option. All right, you will need you will have this option window. You go to EDA tool option and make sure that this one must be this. Yeah, you need to search for this folder Win32ALOEN. So where is that? It is inside this folder, the folder that you install the quarters and in the model sim. And this is the folder. This is inside here. Yeah, this is inside here. The things you install here. This is one time only setting. Yeah. Yeah, inside this model sim. Yeah, model sim ASE, and yeah, this one. Click this and select folder, and you have this. Right. Make sure that you have that. If not, you cannot. You will not be able to simulate later on. Right. But after you have that, you need to do the setting for the simulation. So go to setting, EDA tools, simulation, select model sim altera. Here must be Verilog. Compile the attachment just create a new attachment, and the name of our attachment is FATB, right? You need to add the file, the attachment file, which is this one. Open, click OK. Yeah, you need to add inside here, click OK. Okay, okay, done. Now you can simulate. So to simulate, you go to run RTL simulation and wait for the model sim to be invoked. Right. So it is here. Make it full. Okay, we have error. Yep, we have error. So this is maybe good error because we can learn something from this. Syntax error, unexpected non-printable character with the hex value. Where is that? Can we click that? Because this is because we copy and paste the program from PowerPoint. Yeah. So sometimes these you will have and yeah this thing. Yeah, should be this. Yeah, because this when you copy paste from PowerPoint or from PDF, right? The character here is a little bit different from that, right? Yeah, it should be this. Okay, right. So and the color is different now. See, so it is case sensitive, yeah, for Verilog. So it is better to I mean to simulate this. It is better to before we simulate, we check for the syntax errors first. Yeah, so we do the analysis and synthesis again, so that it will check the test band also. All right, looks good, no error, and now we can do the simulation. Okay, so this is the you can check whether it is correct or not based on the waveform, or you can look at this. Yeah, when time equal time 0, so we have 0 0 0 and C out equal to 0, S equal to 0. Yeah, time 20 we have 0 0 1 and we have S equal to 1. This should be correct, right, based on the output of the full adder. So 1 0 0 we have S equal to 1, C equal to 0 1 0. Yeah, C equal to 0. And if we have 1 1, C equal to 1. Yeah, this is correct. 1 0 1 0 0 we have 0 1, correct. 0 1 0 we have 1 0, correct. 1 1 0 we have 1 0, correct. 1 1 1 we have both 1 1, correct. So this is correct, and this demonstrates how we do the hierarchical design, how we do the simulation. Yeah, which is interesting actually. Now when you know how to do it correctly, right? Okay, from the small design here, we create a bigger design where we call this small design back here to have this. So to have this, and then we have the simulation to prove that the design is correct. Okay, I think that is for today. We now complete chapter 2 already. So next week we will go to chapter 3, and next week also I plan to have a quiz, and it is online, and it will not during the class, so it will be maybe at night. Yeah, I will set the maybe author that you can answer in author and submit your result, your answer. Okay, so that is for today. Any question so far?